Hi everybody, welcome back to Synthetic Biology 1. Today, we'll try for the second time to model growth in bacteria. If you remember, the last time we tried this we were sad, because the model that we came up with didn't work. We did get the essence of exponential growth, bacteria doubling over and over again, but we forgot to include a way to make them stop. In our model, bacteria could just grow and grow forever until they reached impossible population sizes. So let's try it again, but this time we'll be a little less nuts. Here's the original equation that we were using for exponential growth, and here is the new equation for logistic growth. Logistic in the sense of logistics, like managing limited resources. Let's walk through and look at the differences. We still have C, representing the number of cells. We still have R, the specific growth rate. You could imagine, for example, 1 division per hour. The physical unit of R is per hour, or hours to the minus 1. We've also introduced a new term, K. K is the carrying capacity. It represents the absolute upper limit on the number of bacteria that can live in our test tube. It's just what we need to keep our model sane. Let's look closer at the term in the parentheses, 1 minus C over K. Imagine what happens when C, the number of cells, equals K, the maximum number of cells allowed. Well, in that case, C divided by K equals 1, which means that 1 minus C over K is 0. 0 times anything is 0, so there's no growth. In this expression, the logistic term gets smaller and smaller until eventually it forces the entire growth rate to be 0. Let's try some more limit case analysis to see how this model makes us feel. Does it behave nicely, or does it go crazy for some parameters? How about K? What does this model look like when K gets very small? Well, for small values of K, growth stops quickly. Whenever C equals K, growth stops. And if C somehow becomes larger than K, growth becomes negative, meaning that the number of cells decreases. Totally reasonable. Now, what about large values of K? Well, if K is much, much larger than C, then C divided by K will be almost 0. That means that 1 minus C over K will be almost 1. Well, 1 times anything is itself, so the logistic term essentially doesn't affect the growth rate. In this case, the logistic growth model looks very much like the exponential model. The cell production rate equals RC. So how does that make us feel? Well, it makes sense to me. If K is very large, it means the bacteria have lots of space and nutrients, and growth really is basically exponential, at least for a while. Here we have a side-by-side comparison of logistic growth and exponential growth. In this plot, I'm showing the new cell production rate as a function of the number of existing cells. You can see that for exponential growth, new cell production just keeps increasing forever. But in the logistic model, new cell production reaches a maximum and then returns to 0 once the test tube becomes too crowded for new cells to grow. Notice how the two models look similar in the beginning when there are very few cells relative to the carrying capacity. In this case, growth really is exponential. Like last time, this differential equation is simple enough to have an exact solution. And like last time, we can put it in a computer and calculate the number of cells over time. When we look at a logistic growth curve, we can think of 3 phases of bacterial growth. Here, in the exponential phase, cells have unlimited resources, and the growth is almost exponential. Here in the log phase, cells continue to grow, but more slowly. And finally, in the stationary phase, resources are exhausted and growth stops. The logistic model is very close to reality, and it matches well with the growth of real bacteria in real test tubes. To me, it is amazing that we can capture all of that complexity of billions of bacteria growing together with just a simple model of R, C, and K. Okay, until next time, happy growing.
Thank you.